Tree structures generally contain data inside of their nodes which needs to be retrieved. Sometimes we search a tree for a specific value and stop when it is found. And other times we are interested in iterating through all values of the tree, but in a specific order. This video focuses on various traversal orders for tree data structures. The example shown here is an expression tree. This tree represents the mathematical expression, which I'll write down here. What we can see in this expression is that each node in this tree that has an operator represents some value calculated from the left subtree with an operator between that subexpression and the subexpression that corresponds to the right subtree. So we have left subtree, operator, right subtree. If we go all the way down, we eventually have numbers or operands in the leaf nodes. So here we have a left subtree, which is a leaf node with 10. So we have 10 divided by 5. And that is in parentheses. That is a whole subexpression, which is to the right of this multiplication operator, which is shown here. So what if I wanted to write a program that would print out this expression shown at the bottom, given the tree? So I'm given an arbitrary expression tree, and I want code that will print out the corresponding expression in linear form with parentheses, like this. The way I would do this is using an in-order traversal. So an in-order traversal is a recursive procedure that takes a node of the tree. To kick this process off, we would send it the root node. So if I were to call my in-order procedure using the root node of this tree, it would then recursively go through the tree to print out this expression here. How would it do that? Well, let me provide the pseudocode. Basically, we would visit the left, visit our current data, and visit the right. But let's write things out a bit more thoroughly for the sake of printing out this exact expression here. So for any given node we have, the first thing we need is an opening parentheses. This is something that's unique to this expression tree problem. Then, if there is a left subtree, we're going to recursively traverse that in order. So if the node has a left child or a left subtree, then we call our in-order procedure recursively on that left child. Regardless of whether that happens or not, the next thing we do is print the data in the node. So the data inside of this node is the plus sign. The data inside of this node is the 3. Next, we would visit the right node, if it exists. And once we visited any right node that exists, we would have to print a closing parenthesis. This is once again unique to this expression tree problem. In general, in-order traversals are very common, and they don't only apply to expression trees. But the steps that are essential for an in-order traversal are simply visiting the left, then doing some sort of operation on the data in the current node, and then visiting the right. And so those are the fundamental steps in an in-order traversal. Visit left, evaluate data, visit right. We call it an in-order traversal because this crucial step of actually manipulating or otherwise using the data in the node occurs in between the left and right visit steps. Let me go ahead and show you what this traversal order looks like when executing on this tree. So if I call in order with the root, I would be here. However, the first thing this code does after printing the parenthesis, so we would print that parenthesis there, is check the left node. So we go to the left. Well, once we're at the left node, we print parenthesis, it's the second thing we do, and then we go to the left. So we're here now. We print a parenthesis for that one. Then we go to the left. And then here, technically we would be printing, given this code, extra parentheses around the individual numbers, which is something we could tidy up if we made this code a bit more elegant. I'll just leave it in for simplicity now. It doesn't make the expression wrong, just a bit ugly. So we print a parenthesis on the left side of that. But then there is no left node. This is a leaf. So because this is a leaf node, we have no left child. We don't do that step, and we go straight to printing the data in the node. Well, the data here is 2. And so that's why a 2 gets printed out here. And then there is no right node, so we skip that, but we do print this ugly extra parenthesis there. And then we finished executing this procedure at the level of this node. So the very first place we visited was here. And the question is, what prints out next? Well, we see from the expression that we should print out this multiplication. And so that's what's going to happen, but the question is why? Well, this node was to the left of the multiplication. So when that procedure call finishes, we jump back to this spot in the code. We just returned from this call Inorder node.left. And so the next thing to do is to print the data in the current node, but the current node will now be this multiplication. So that gets printed out next, and we've basically gone from this node to this node. And from this point, we go to the right. So we go to the right, but from here we go to the left, and we have a parenthesis for that. And go to the left again. There's nothing there, so this is the parenthesis for the 10. But then we print the 10. Oddly enough, that's the 10th thing we print. That's nice. It has a parenthesis around it. There's nothing to its right. So we go from here to here. And then we return. And once again, we got here by going to the left. So the next thing we do is print the data in this node, which is the division. Then we go to the right. We print parenthesis here. We would go left, but there is no left. So we print the 5 next. There. We would go right, but there is no right. We do print an extra parenthesis there. And then we have the closing parenthesis for the division. And then the closing parenthesis for the multiplication. And then we're returning from all these right calls. So after printing the right, we printed a parenthesis, return, printed a parenthesis, returned. We finally get to a point where we return back to this node that has subtraction in it. That was a call to the left, so now we can print its data. So from here, we print the minus, and this procedure continues. I will draw the remainder of these arrows rather than sort of painfully go through all the steps, but it's the same process over and over again. If there's a left, visit it, print the data in the current node, then if there is a right, visit that one. And eventually we get through all of this and we're done, and we'll get a result that looks like this. And here we have the final traversal order, which matches the sequence of operands and operators shown in this infix expression below. We go all the way to the leftmost child first, before then going up and printing that node's parent, and then we handle the right child or the right subtree, but within each subtree that we print, we always go all the way to the left first. So we do the 2, we do the multiplication, but then in the right subtree we have to go down to the 10. The division, then the 5, and then we can go all the way up here to the minus, because that was the parent of this subtree here. And we eventually get through all of this to have this final ordering, which involved printing 39 distinct things if we include these superfluous parentheses around the individual operands. However, there are other tree traversal orders. When it comes to arithmetic expressions specifically, we know that one way of organizing the operators and operands that does not require the use of parentheses is a prefix expression ordering. And interestingly enough, there is a tree traversal order called a preorder traversal, which corresponds to a prefix expression when applied to an expression tree. So a preorder traversal has the same steps as an inorder traversal, it just rearranges them. In a preorder traversal, the very first thing we do is visit the data in the node that we're currently in. And in the context of this expression printing problem, visiting the data means printing it out. So we will first print the data in the node. And then after printing / visiting the data in the current node, then we will go left and right. So this is the pseudocode for a preorder traversal. And notice that we do not print any parentheses. As I mentioned, a prefix expression does not require parentheses. And so this preorder traversal will not bother printing those out. So let's actually execute this on this tree and write out what the expression is as we go through the tree. So if we do a preorder call to the root node, the very first thing we do is we print the data in that node. So we immediately print a plus. And then there is a left node, so we go to the left. So now we're at the beginning of a new preorder call, but we're focused on this node here. So we've already visited / printed the plus. Now we go to the left. Well, the first thing we do is we print node.data. So we're going to print that node's contents. So plus and then minus. And then we'll go left from there and we'll print the data in that node. So from here we go to multiply, print out, and we go to the left and print the node data. So we have our first operand, which is a 2. And then at this point, this node does not have a left child, so we do not do a preorder recursive call. It does not have a right child, so we don't do a preorder recursive call to the right. That means that this call finishes, it terminates. We go back up a step. We reached this node from the left, so we're now at this point in the code after having finished the preorder call to the left. So now we do a preorder call to the right. So after the 2, the next thing we print is this divide. So we jump to there next. So there's a division. And then we go to the left from there. There's the 10. No left, no right, so those calls don't happen. We return back up. This was reached from the left, so now we go to the right and print the 5. And then at this point, we return to the division, but we finished the right call, so that call finishes. We go up a level to the multiplication, but that was to the right, so that call finishes. Go up to the subtraction, that was a call to the left. So now we can go to the right of the subtraction node. So the thing that follows this 5 is that 3. Then we can't go left, can't go right, so we return. We've already gone to the right there, so we return. We went to the left from the plus, so now we go to the right, and then we visit that node immediately. So from the 3, the next thing we do is print out that plus, and then we go down the left side and print those nodes' data as we encounter them. No left, no right. Go to here. And then back up to here, and then down there. Have 7 at the end. So this is a prefix expression that is generated by doing a preorder traversal of the nodes in this expression tree. Now, it is also worth noting that these traversal orders are not only used for expression trees. And I mentioned earlier that sometimes we want to iterate over all the nodes, and sometimes we want to search for a specific value. So let's say, rather than wanting to print out this expression, I just wanted to visit the nodes and then stop as soon as I found, let's say, a division operation. Well, that would correspond to going here, 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 and then finding that division operation and then stopping. That would be an example of something called depth-first search, often abbreviated DFS. Now, strictly speaking, depth-first search doesn't care whether you always go to the left first. I could always go to the right first, and as long as I had this general approach of visiting the node data before then doing recursive calls on all possible children, that would be an example of depth-first search. But essentially, preorder traversal is an example of depth-first search. Depth-first search itself is a bit more broad, and once again, we typically terminate as soon as we find the thing we're looking for, but you can think of preorder traversal as being an example of depth-first search. Now, going back to mathematical expressions, you should know that if we have a way of generating a prefix expression, then we must also have a way of generating a postfix expression. And sure enough, we do. That will use a postorder traversal. For a postorder traversal, we once again reorganize the same steps, visiting the left, visiting the right, and printing / accessing the node data. So in this case, because it is a postorder traversal, the actual visiting of the node data or the accessing of the node data is the thing that comes last after going left and right. But that's the only change. We just move the position of this print node data statement from being before the recursive calls to being after the recursive calls. That results in the following traversal order and corresponding output. So if we call postorder on the root, we would go left, and then go left, and then go left. We haven't printed anything yet. It's only once we reach this leaf node that we would fail to go left, fail to go right, because we don't have left or right children, and then we would finally print something. So the first thing we would print in our postorder traversal would be the 2. And then, because we've just returned from this, we would then have finished a call to the left, while accessing the node with the multiplication, but we have to go both left and right before we print that node value. So from here we'll go to the right, and then from here we'll go to the left, and then there are no children here, so we fail to go left, fail to go right, and then print the 10. So the 10 follows the 2, and then we go back up to here. That was a left call. We now go to the right. From the 5, there is no left or right child, so we print out the 5 after those recursive calls fail. And then, once we return from the 5, this is going to be the first operator we print. So this node has already had its left tree explored and its right tree explored. So now we can print the node.data for that particular node. So we have division there. And once we return to the multiplication, the same is true. We've gone to both its left and right children. So now we can print the multiplication. Then from here, we return up. We have to go to the right before we can print the minus. So the next thing that comes out here will be the 3. And now we've gone left and right, so when we return, we'll actually print out the minus. Here, we've finished exploring the left subtree of the root node, but now we have to go to the right, and once we call the right, we then go to the leftmost child of that whole subtree. So the next value being printed out would be this 3. And then the 10, and the multiply, and the 7, then the plus, and then finally the root node gets printed there. So here we have a complete postfix expression. This is the traversal order, and hopefully this is clear, but I just want to emphasize that all of the traversals we've done, so the in order, the pre-order, and the post-order, although they produce different expressions, when you evaluate those expressions according to their own rules, so you evaluate the postfix expression like a postfix expression, or you evaluate the prefix expression like a prefix expression, they will all evaluate to the same result. So we're simply taking this data and expressing it, processing it, traversing it in different ways, but we're not fundamentally changing it. However, there is one traversal order I want to teach you that is somewhat fundamentally different, and that is a level order traversal. So this traversal order doesn't really make sense in the context of the expression tree that I have here, though it is useful in other contexts, and so I'll simply present it using the same tree I've used in the other examples. Basically, a level order traversal simply starts at the top of the tree, the root, and prints out or visits the data in the nodes one level at a time. So that'll look like the following. We will visit the root first, and so if I'm printing these values, I would print a plus, and then I would print everything in the next level down. So I would go to the minus, and then to that plus. And then I would do everything in the level beneath that. And so from here, I would go to that multiply, and then the 3, and the multiply, and then the 7. So everything in that order. Now the next level. So from here, the first thing on that level is the 2. So we would have 2, then a division, then a 3, then a 10. And notice that we don't care if some parts of the tree don't reach that given level. So like this particular node had no children, and so nothing beneath that reaches the level that all these other nodes are at. But that's irrelevant. We simply go one level at a time and then go from left to right within that level. And the final level in this tree is here. And so we would finish with another 10 and then the 5. And so this is a level order traversal. And the code for this is somewhat unusual because it is not recursive, but I'll go ahead and show it to you. It uses a queue data structure. So this is the pseudocode, and the general idea here is that we're going to put a node, initially the root node, onto the queue with the enqueue operation, and then we're going to loop as long as that queue is not empty. On every iteration of the loop, we're going to remove something from the queue. We will dequeue the value that's at the front and put it in this temporary variable n. We'll print n's data, so we're visiting the node that we just dequeued, the one we removed from the queue. But then we're going to put all of the child nodes of the node we just visited onto the queue. So if n has left, we enqueue that, and if n has right, we enqueue that. So this is kind of similar to things we've seen before. And it turns out that this process will give us this level order traversal. Let's just go through a few of the early steps to get an idea of why this is the case. So if we start a new queue and we're starting from the root, then the first thing that we will enqueue will be this plus sign. So we've enqueued the plus, and then we immediately, in this loop, dequeue the plus, and we print it out. So I'm going to use a circle to indicate that we've put it in the queue, and I'm going to exit out once we've printed it. So we print out the plus, that's done. But after printing it out, we then put its two children onto the queue. So we do its left child first and its right child. So that loads up the subtract, which is right there, and the plus, which is right there. And then we go to the next loop iteration. We dequeue the thing that's at the front of the queue. Well, that'll be this minus. So we've printed this right there, print in.data. And then we put the left and right child of the minus onto the queue. Well, the left and right child of the minus are the multiply and the 3, and sure enough, those are the next things in order here. On the next iteration, we print in.data, that's this plus there, and so now we'll put this node's children on the queue. Well, that's multiply and 7. So put that on the queue, put that on the queue. Next iteration, dequeue this multiplication, that's right there. We print it out, and then we put its children on the queue. 2 and divide. So you can see that this order that I'm expecting is matching this code that I wrote afterward. And I'll go ahead and carry out the rest of these steps, but hopefully you're seeing the pattern and you're understanding how this works. So once we get rid of the 3, notice that 3 has no children, so nothing gets added. We just, oh, sorry, that's this one. We just print that 3. So this 3 has no children, so we just print that 3. When this multiplication comes off, we add the 3 and the 10 that are beneath it. 7 comes off, we print it, but we don't add anything on. 2 comes off, we print it, but we don't add anything on. Division comes off, we print that, we add the 10 and the 5. Then this 3 comes off, we print it, that 10 comes off, we print it, this 10 comes off, we print it, this 5 comes off, we print it. And so because all of those things were leaf nodes, we didn't add anything to the queue. And at this point, the queue is empty and the loop exits, and we're done. We've completed our level order traversal. So this is an interesting demonstration of how you can use a data structure from earlier in the course to do a tree traversal. And I'll also make a note here that if you wanted, you could do a similar thing with, for example, a pre-order traversal using a stack and get the same result. So that would be a way of doing a pre-order traversal with a stack that would be a non-recursive way of doing a pre-order traversal. The last thing that I'll tell you before wrapping up this video is that this level order traversal is actually an example of something known as breadth first search, which is often abbreviated BFS. So I mentioned depth first search earlier. Breadth first search is also a search technique, and therefore it typically terminates if you find a specific node. And so if I were looking for a 3, for example, this one would be what I would find. I would still visit the nodes in this order. I would simply stop once I found the 3. The other thing I'll say about breadth first search is that it is more general than a level order traversal, because the level order traversal specifically cares about going from left to right, whereas in a breadth first search, all I really require is that I visit all of the children of a given parent before I visit anything at a level beneath that. So the breadth first search order could visit, for example, this node, then that node, before, change the order of those two. And then for this level where we have these 4 things, if I were to visit, this one, then this one, then this one, then this one, that would also be acceptable as long as I visited everything at this level before I visited anything at this level. So small distinction, but for simplicity's sake, simply think of level order as being roughly equivalent to breadth first search.